I'm going to give you a sketch of the proof of the Cauchy integral formula, which roughly, without the hypothesis, says 2 pi I times f of w, where w is this bad point right here, is equal to the integral of f of z over z minus w. So f is the numerator, w is the bad point in the denominator, so on and so forth. And the key point here is that the Cauchy's theorem says that any two circles centered at w are going to be holomorphic, are going to be homotopic, and this function here is going to be holomorphic everywhere except for w, which means that if I can form an open set, which is the outside of the circle, and on that open set, this whole integrand is holomorphic, which means that if you have two circles, they're going to be homotopic, which means that the integral over the big one r is equal to the integral of over the little one little r. And we're going to use that. We're going to basically let little r go to 0, and we're going to see what happens. So the method of the proof is going to use that, and the method of the proof is essentially there are two ways of proving that the limit of x squared is 2x. You could either do it like that, or you could do it the limit of x squared minus x naught squared over x naught, or x minus x naught minus 2x naught equals 0. We're going to prove it by using this approach. We're going to show that the difference between what we have and what we want goes to 0 as r goes to 0, little r. So here's basically what we need to do. We need to show the limit as r goes to 0 of the integral over the big R, the one that we're given in the problem, minus 2 pi I times f of w. We're going to show that this equals 0. And how are we going to do that? Well, we did this in class. 2 pi I is equal to the integral of the normal integrand here minus the integral of 1 over z minus w, and then I still have to multiply times f of w, like so. So this part didn't change. So this is equal to, over the big one, I'll rewrite it again, f of z over z minus w, I'm going to drop the dz though, minus f of w here is a constant because I'm integrating over z, so I can pull it inside z minus w. Oh, by the way, there should be limits here. Limit. And then this is equal to, now I have two integrals. With this basically same denominator, I can combine them and just say that this is equal to limit as r goes to 0 of the integral f of z minus f of w over z minus w. Great. Well, so now I can use the fact, sorry, I should have done this before. The integral over c big R is the same as little integral over c little r by the argument I set up here, originally set. So now I have both the integrals are over cr. So now I have the limit over the little circle of this is equal to this, and hopefully that's going to go to 0. Well, the limit, this integral is less than or equal to the maximum value of z minus zw over the circle times the length of the circle, which is 2 pi little r. So this is the maximum value over that, which we can simplify. Right? We can simplify this is just going to be, that should be a length. We can simplify this down to z minus w on this little circle is just literally equal to r. It's the max of f of z minus f of w equals r. Because the circle, this red circle is defined by z minus w equals r times 2 pi r equals the max of f of z minus f of w times 2 pi. But the max here, as r goes to 0, these are going to be the same points. That's 0 times 2 pi equals 0 as you take the limit. These